All right, so let's take a look at our lesson for today. This is our second lesson on alternating series, and this lesson is kind of focusing on the alternating series remainder. Let's just remind ourselves what that means, what it means to be a remainder. A remainder is the error. It's just a fancy word for error. So we want to be able to, when we're approximating sums of series, it's important for us to be able to determine what error our approximation is, and this is how we would do it with alternating series. So first up, we would need to basically show these three things. The series has to converge before we can determine an error. So we have to show the terms are alternating, decreasing in magnitude, and have a limit of 0. So this would be like number 1, 2, 3 things that you would have to physically write out to use this error bound. You have to write those 3 things. This is what allows you to use the error bound. So that means that the series actually is going to converge to a sum S. This S is actually the for real sum. This is the real actual sum, not the approximation. S, just a plain S, is the real sum. And what we would do is we would approximate S by a partial sum. You know, we would decide, or usually we're told, well, not always, how many terms to use. Do we use 5 terms? Do we add up the first 5 terms? How many terms are we going to use to approximate the sum? That's the partial sum. The error in the approximation, the error is R sub n, and n stands for the number of terms you've used to approximate. So R sub n means error. Okay, it means error. And this is a different way to write error. This means, this is called, this is just a different way to write error. S, we talked about S just a few moments ago. This is the real sum, and this is the partial sum. And I think that makes sense, makes intuitive sense, that if I knew what the real sum was and I subtracted the partial sum from it, then I would figure out what the error is. So that's just another way to write error. You can write R sub n, well, the n is an actual number, or you can write S minus S sub n, with n being, you know, a number. And here's the beauty of this error bound. This is a very easy error bound to use, because you basically, the error will be less than the absolute value of the first omitted or truncated term. That is very powerful. The first omitted or truncated term is the next term. And what do I mean by next term? If you used, say, 10 terms to approximate the series, the 11th term would be the error bound. It would be the first, or just the maximum error, the first omitted or truncated term. All right. So in other words, this is just saying it a different way. In other words, if those 3 conditions are met, you can approximate the sum of the series by using the partial sum, and your error will be bounded by the absolute value of the first truncated term. This is called your upper bound. Okay, so that's the concept behind what we're getting ready to look at. Are there any questions about the concept? Okay. We have a couple of examples that we're going to work through. Your calculator, it would be handy for you to have your calculator. If you don't, you can just watch on. But we want to look at a few things. So approximating the sum of the series by using the first 4 terms, we can totally do that on our calculator. And so I want to pull our calculator up. I would do the calculator part. Now, just to get to the summation, the sigma notation, you can click this button right here, the palette O Math, and there's our sigma notation right here. I like to use these gray buttons for variables that will not steer you wrong. So I'm going to say we're just typing it in, x equals 1. And it says approximate by using the first 4 terms. So I'm going to go from 1 to 4. 1, 2, 3, 4. That's 4 terms. Please be careful what the starting number is. Like if I started at 2 and I wanted 4 numbers, I wouldn't go to 4, would I? If I started at 2, I would go to 5. Or if I started at 0, would 0 to 4 be 4 terms? No, it would be 5 terms. So just please be careful that to do whatever they're asking you to do, be aware of where you're starting. So I'm going to put a fraction in there. So we've got, what, -1 raised to the, and I'm just using x's, x plus 1 over x factorial. The factorial, there's probably an easier way to find it. Where I found it was menu probability factorial. I wish there was an easier way for it. I don't know, maybe there is, but we can look at that later.
There's one right next to the G. You just press on it.
Oh, perfect, by the G. There we go. There's one right there. Okay, so then we hit enter, and that gives us our sum of 5/8. All right, so let's go to our document. And so we would say S sub 4 equals 5/8. Okay, so what I want to do also, though, while we're working with the calculator is I want to look at a way that you can list the terms, because that's going to be kind of important to us when we are looking for how many terms, let's say, how many terms do we need to use so that our error is, less than 1 over 100 or something. How many terms? So that's going to be helpful for our calculator to list the terms for us. So I'm going to show you how in your calculator you can just list. So we'll just stay with this one. And let's just list, just for fun, I don't know, whatever the first 10 terms. Okay. So what we do is, it's a sequence. Now, I don't know if you've ever gone to this book thing right here. This book thing right here, if you type in S for sequence and then scroll down, it's right here. There's the sequence, and it tells you how to put it in. So to list the sequence, we need to put the expression in first, comma, the variable, comma, the low number and the high number. And then if the step is something other than 1, in other words, what if you wanted the first and the fourth and let's see, first, third, fifth, or something like that. What if you wanted every other term? Well, you could put that here, this different step. So you can hit enter here and pull up sequence, or you can actually type in SEQ and it'll do this too. So we want to put this in. All right, so we're going to do here, I've got what we do, -1 raised to the x plus 1 over x factorial, and we'll use this fun button. And so that's the expression, comma. Then we want to use the variable x, comma. We want to start with the first term, comma. And we want to go to the 10th term, just for fun. And I'm going to look at every term, so I don't need to put a comma and a number there. So that's just going to spit out the first 10 terms, which is very helpful for us in this unit, just so we can see what the terms are. Okay, so I'm going to write that on here so we just have a list of it. So we would do SEQ, and then we would write like -1 to the n plus 1 over n factorial, or in our calculator we'd use x's, n comma 1 comma 10, and that would give us the first 10 terms. So this just lists the first 10 terms. And that's going to be very helpful for us as we move on into this lesson. All right, are we okay with the calculator input? Okay. So we've done part A, we've approximated the sum. So this is partial sum, the fourth sum, using the first 4 terms. Great. Part B, explain why the estimate found in A differs from the actual value by less than 1/100. This right here differs from the actual value. This is talking about error. Those are words, weird words that are asking about error. And so, okay, we can deal with that, right? So we need to use, this is an alternating series. And so let's go back to our calculator and look at what the fifth term is. So 1, 2, 3, 4, here's the fifth term. The fifth term is 1/120. Is 1/120 smaller than 1/100? Yes. So looking at this, let's just talk big picture. Looking at the alternating series error bound, we can certainly verify that's true. Now, we have a lot of reasoning that we need to write out to show that. We can't just write, yeah, it's 1/120. We can't write that. So what we have to do is we have to first say why we can use it. Why can we use this error bound? Well, since the terms of this series number 1, alternate. Number 2, decrease in magnitude. It's important to say decrease in magnitude because you know they go back and forth, plus, minus, plus, minus. It's really important to say they decrease in magnitude. And 3, have a limit of 0. We can use alt series error bound. Now, the most important things to say, so what words could you leave out? You would just need to say this series alternates, decreases in magnitude, has a limit of 0. That's non-negotiable. The other part is just explaining your position. So what do? Now we write up. We have a couple of options. We can say absolute value error. This is actually my favorite. Absolute value error. That's my favorite way to write it. Okay, or you could say, you don't have to say all of these. I'm just showing you which things can you say. Or you could say R4, the remainder 4, which means the remainder of after using fourth terms, or the error after using fourth terms. You can say it that way, or you can say it this way, S minus S4. Okay, those 3 are interchangeable. You can use either one of those that you want. But you also need to be able to recognize them. If you see them in writing, you need to understand what that means. And so what we're going to say is that the alt series error bound, because that stuff in the box is true, therefore the error is going to be less than the fifth term. Okay, so that's just talking about what we're getting ready to show. This right here is simply highlighting our concepts. I'm getting ready to write down what you would write to this is what we're thinking through. So now the way that I would write it for this problem, I would say absolute value error, because that's my favorite one to use. It's so easy. Is less than. So our fifth term, we just looked it up. It was what, 1/120, right? Which is also less than, which is less than 1/100, because that's what they were, wanting us to describe. And so this is our actual answer right here. Okay, so this right here is what you would show. So the two things you have to write are the things in the pink box and that thing right there on a problem that I give you. The other stuff is explanations. Okay, are we okay so far? All right, so the last part says use your result to explain why. Why is the sum? Now S, this S means the actual sum, right? That's the actual sum. Why is the actual sum, why can the actual sum not be 0.7? Okay, well, it can't be 0.7, that's what they're saying. So this is what we need to think. So we would take, and this is the thinking process I'm going to write up here. So we would take our partial sum and subtract our fifth term, right? Because the fifth term was the error bound. And that's going to be less than the for real sum. And that's going to be less than the partial sum plus the fifth term. What this is giving us, is what we call an error bound. So it's telling us exactly where, and it's given us the bound of what our for real sum could be. So this part right here is explaining what's going on. Okay, so let's show what would we write if we were asked that. So I would take my 5/8 and I would subtract the fifth term, which was 1 over 120. And so I really, since this is a decimal right here, I really need to put this in decimal form. I want you to understand what I'm doing. I'm getting ready to write it as a decimal. So when I do that, I get 0.617. And then I would take my 5/8, which was my partial sum, and I would add my error. And that gives me 0.633. So that is the range that my actual sum, the for real sum, could be in. Therefore, the actual sum cannot equal 0.7 because 0.7 is not in that interval. Okay, so what have we done so far with error? We have used the error bound to prove that the error is actually less than 1 over 100. We did that in part B. And in part C, we actually found the interval that the for real sum could be in. And we could verify why, something can't be the sum. All right, questions so far? Okay. So we have one more example. In this example, we want to know how many terms are needed to approximate the sum of the series so that the estimate differs from the actual sum by less than 1 over 100. Okay, so this is our big deal right here, 1 over 100. So, okay, why don't we go to our calculator? We're going to do this sequence thing. We're just going to print out, so I don't know. I don't know how many. We could do it by hand, but why when you have a calculator? So I'm just going to bring this down and I'm going to change it up to fix it. So let's see, it's -1 to this, so that's right. Down here we need to do, so x to the 4th. And the first 10 terms are fine. I don't know how many it's going to take. Why don't we just list 10 terms out? Okay, so there's our list. And what did it say? We wanted it to be the error less than 1 over 100. So how many terms is that going to be? What term is the first term that's smaller than 1 over 100? The fourth term is the first term that's smaller than 1 over 100, right? So that means we need 3 terms. We need 3 terms so that our error would be less than 1 over 100. Is everybody okay? Okay. So we would say, well, let's just start our writing. So the real sum would be about, the first term plus the second, which is actually minus, plus the third, and then minus, and then the fourth, plus dot, dot, dot. This, I don't know who named it this. It's kind of interesting. This is called, someone called this stop and chop. Okay? So we list out our terms. We just used our calculator to do it. It's not like we had to do a lot of work for that. And we go until we get to a term that's smaller than 1 over 100. And then we stop and chop. So what does that mean? That means that we need 3 terms. 3 terms are needed. And again, whenever you use error, you have to justify. Can't just assume that you can use this scenario. And we've done a lot of alt series, and I didn't stop over here to talk about why this was convergent. The series alternates, it's there. It decreases in magnitude. Yeah, that bottom gets bigger and bigger. Has a limit of 0. The nth term does. So same thing here. This series alternates. So since the terms number 1 alternate, and you can abbreviate alternate as ALT. Number 2 decrease in magnitude, and you can do some abbreviations. DECR, decrease in magnitude. Now you can't do like acronyms. Please don't do any acronyms unless they're like MVT, because we won't know what you're talking about. 3 have a limit of 0. By alt series error bound. Now we're going to do my favorite way. Sorry. My favorite way is absolute value error. Why is this my favorite way? Because I don't have to think about the number. It just makes me happy. Which is less than, and what we said our 4th term was 1 over 256. Gosh. 256. And it is less than our required 1 over 100. And we got it.